Quantum computers are often described as machines that try every answer at once. That picture is catchy, but it is also misleading. If a quantum computer simply held many possibilities and then revealed one at random, it would not be very useful. The real trick is subtler. It stores information as amplitudes, changes those amplitudes with gates, and uses interference to make wrong answers cancel while useful answers become more likely. The best mental model is not a billion tiny computers running in parallel. It is one carefully controlled wave, evolving until a measurement is likely to reveal something useful. Start with the smallest unit, the qubit. A classical bit is either 0 or 1. A qubit has two basis states too, called ket 0 and ket 1, but its state is a weighted combination of both. The weights are amplitudes, usually written alpha and beta. Their squared magnitudes become measurement probabilities. The block sphere is a visual shorthand. North is 0, south is 1, and every point on the surface is a valid single qubit state. The arrow on that sphere is not a physical needle. It is a compact way to remember two facts at once: probability and phase. A quantum gate does not copy a qubit or inspect it. It rotates the state. The Hadamard gate is the first important example. Applied to 0, it produces an equal superposition, half the probability on 0 and half on 1. But it also controls phase, the sign and angle of the amplitude. Phase is invisible if you measure immediately, yet it becomes decisive when paths later meet and interfere. This is why the same probability distribution can behave differently after more gates. The hidden phase information has been preserved. Measurement is where the quantum state becomes a classical answer. If the state has equal weight on 0 and 1, repeated runs produce a roughly 50-50 histogram. One run gives one bit, not the whole hidden state. This is why quantum computing is not free exponential parallelism. The algorithm must shape the state before measurement, because after measurement most of the information is gone. With 2 qubits, the state has 4 amplitudes: 0, 0, 0, 1, 1, 0, and 1, 1. With 3, it has 8. With n qubits, the state space has 2 to the n amplitudes. That exponential state space is why quantum systems are hard to simulate classically. But a quantum computer still cannot print all 2 to the n amplitudes. It can only transform them with gates, then sample from the final distribution. The moment 2 qubits interact, something new can happen: entanglement. A simple circuit makes a Bell state. First, put the top qubit into superposition with a Hadamard gate. Then use it as the control of a controlled NOT gate. Now the 2 qubit state is a combination of 0, 0 and 1, 1. Measure many times and the results are random but perfectly correlated. The engine of a quantum algorithm is interference. Amplitudes are not probabilities yet. They can be positive, negative, or complex. When 2 computational paths meet with the same phase, they reinforce. When they meet with opposite phase, they cancel. A good quantum algorithm is a carefully engineered wave machine. Arrange the computation so bad answers destructively interfere and the useful answer constructively interferes. This explains why famous quantum algorithms feel so strange. Grover's search repeatedly marks a target and reflects amplitude so the marked answer grows. Shor's algorithm turns factoring into a period-finding problem, then uses the quantum Fourier transform to make that period show up in measurement. Quantum simulation is even more direct. Use a quantum device to mimic another quantum system, the use case that originally motivated Feynman and Manin. There are limits. Qubits are fragile. Noise leaks information into the environment, destroying the delicate phase relationships the algorithm needs. Real machines use calibration, error mitigation, and eventually quantum error correction, where many physical qubits protect one logical qubit. So a quantum computer is not a faster laptop. It is a specialized machine for problems where amplitude, entanglement, and interference match the structure of the task. That is also why engineering progress matters as much as algorithm theory. Deeper circuits only help if the machine can keep them coherent long enough. Here is the mental model to keep. A qubit is an amplitude vector, not a fuzzy bit. Gates rotate that vector without measuring it. Entanglement lets multiple qubits share a state that cannot be split into independent parts. Interference is the payoff. The algorithm is useful only when it moves probability mass toward the answers we want before the final measurement.